Okay, welcome back to video 2. So on the front side, we decided, or we sort of thought about how do you think about if you have interest that's compounded annually, so once a year, and the interest that you make, you reinvest. And so now it's not only your original investment that's making money, but the interest is making money. And then the interest on your interest is making money, and so on. And the general equation we derived was principal times 1 plus the interest rate raised to the number of years, or the number of times we're compounding. Okay, so on the back, let's ask a different question. So I said in the front that we're compounding annually. So we're getting our interest fed back into our original investment once a year. What would happen if it happened twice a year? So what would happen if we computed the interest after 6 months and then put our interest back in, and for the second 6 months it was also earning interest? And then what if we did it even more? What if we compounded every month? How can we think about that? So to simplify the situation, let's say that we're just going to invest $1, and we're only paying attention to how much money will we have at the end of 1 year. But we're reinvesting our interest multiple times over the course of that 1 year. And again, let's say that we're experiencing 100% interest. So let's kind of sketch a little picture and kind of push our intuition in a direction. So this is going to be time, year 0, year 1. Here's money. So here's my $1 that got invested at year 0, and then it's just kind of sitting there in the bank, and then at the end of 1 year, I've still got that $1, but it's generated 100% interest. So here's the second dollar that's my interest. And so now at the end, I have $2. Okay, what would this look like if we compounded twice a year? So let's draw the same picture. Here's money, here's time. So at the end of 1 year, I've still got my original $1 investment. But this time, halfway through the year, I've still got my $1 investment, but I'm going to have my interest calculated. So if I'm still at 100% interest, it's like I'd get, by the end of the year, I still need to have $1 worth of interest. But after 6 months, I'm going to get half that, and then I'll get the second half at the end of the second half of the year. So instead of getting my whole dollar all at the end, I'll get kind of like a $half here, and then so then that $half is kind of still sitting there at the end of the full year, but then I get my other $half. So this is interest on my original investment, and then this is interest on my original investment, and so you can see that's the same as the previous situation. But because I got a $half after 6 months, I can reinvest that $half right here at 6 months. And so now that $half is earning 100% interest for the remainder of the year. So how much interest is that $half going to make over this 6 months? Think about it for a second. So if it was a whole year, the $half would earn a $half of interest, but this is only a half year, so my $half is going to earn half of its own amount in interest. So we've got like a little $quarter here. So if I add them all up, I've got original investment $, I've got interest $, and then I've got interest of my interest, and so I've got $2.25. So here I've got $2, here I've got $2.25. Okay, so what happens if we compound every single month? Whoops, not 12, it's still 1 year, but like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Wait, did I screw this up? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. So I've got my $1. And then after 1/12 of a year, I should get 1/12 of my interest. So I'll have my $1 plus 1/12 of a dollar. And then in the next month, I'm 2/12 of the way through the year. So I get another 1/12, but that original 12th is earning interest. So I'm not going to draw this whole picture because you can imagine how crazy it's going to be, but it's like each time we earn a fraction of our overall interest, we're putting that back in, and now that fractional amount is earning interest. And so we're just going to get money, 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 money But now the question is how much? When we compounded twice a year, we made an extra quarter. If we compound 12 times a year, we should be earning a lot more. I don't know. And like computers, all money is digital now, so there's no reason why the bank couldn't compound once a day, or once a second, or once every millisecond, or once every nanosecond. So that's what we're going to think about is, let's imagine that we're compounding more and more frequently. What's the theoretical maximum amount of money that our $1 could make by the end of 1 year if we were compounding as frequently as possible? So let's do this. I should have made this table differently. So when we compounded once per year, we ended with $2. And when we compounded twice per year, we ended up with $2.25. Why don't you by hand calculate what happens if we compound 3 times a year, because that'll help you think through the scenario. And then why don't you pay attention to the structure you're using to do this calculation and make a guess at 12, or see if we can write an equation in general. So spend a minute thinking about that, and then we'll do it all together. Okay, we're back. So hopefully you made a connection between this page and the front page. Here's the connection that I'm seeing. So you can think about this as we're getting half of our interest twice and reinvesting. So if we didn't want to think about this as 1 year, if we wanted to think about this as how many times are we reinvesting, we could think about this as, like, on the front page, instead of having an interest rate of 100%, we have an interest rate of half that over 2 years. So you could, like, that should be the same. Why don't you think about that for a second? So based on the front page, we had this, P times 1 plus R to the T. So here our principal is just $1. So 1 plus the rate of return to the amount of time. So what would happen if we invested at a 50% rate of return for 2 years? This is describing exactly what we've done here. Here we are getting a 50% rate of return on our $1, so we get our 50 cents, and then we reinvest that, and we have that making 50% returns on the next 6 months. So instead of thinking about this as T, years, we can think about this as number of times you reinvest. So number of time intervals, but not necessarily years. So if we're thinking about it that way, 3 should be calculated this way. It should be our initial investment of $1, and then 1 divided by 3, because we're getting 33.33%. We're getting a third of $1 as our rate of return. And we're reinvesting 3 times. And so if we work this out on the calculator, we get $2.37 approximately. There's some extra decimals out here. Okay, so why don't we try it for 12? Why don't you, and then, like, for n, we already know what it is for n. For n, it's 1 plus 1 over n to the n. So why don't you try and answer our question? What is that theoretical maximum? Plug in bigger and bigger numbers and see what does it seem to be doing. Okay, well, I don't know why I would do it on the calculator. So here I've written our general equation. We've got 1 plus our 100% rate of return divided by n times we're compounding per year. And then to the power of n, because that's how many times we're compounding per year. So now let's look at this for different values of n. So compounding once a year, we get $2. Compounding twice a year, compounding 3 times a year, 4 times a year, 5 times a year, 6 times a year, 7 times a year, 8. So if you look at what's getting plotted, we don't actually have to go to compounding hundreds of thousands of times a year, even just 72 times a year. Our return seems to be leveling out. So what is this horizontal asymptote that we seem to be approaching? It's like 2.69996. Let's go ahead and plug in a very large number. Well, not that large. Okay, so what if we compound 1,000,000 times a year? 2.71828. So hopefully you remember from the very beginning of the lesson what I promised it was going to be about. That number that we are approaching is e. So in general, if we have the limit as the number of times we're compounding approaches infinity of the amount of money that we'd have, that is the definition, or that's one of the definitions of the number e. So conceptually, you can think of e as this sort of theoretical maximum. It's like the speed of light, like nothing can go faster than the speed of light. So you might try and make more and more money by compounding more and more frequently, but even in the abstract limit where we're compounding continuously, you know, not every nanosecond, not every picosecond, even faster than that, just continuously. E is the theoretical maximum amount of money you can get if you invest $1 over 1 year at 100% interest. So that might seem like maybe it's a little weird that we would name this seemingly very specialized situation, like we would say, oh, that's E. E is so important because it describes this artificial seeming scenario. But the important thing to realize is E describes this kind of base growth rate for any process that is growing continually. Over here, our money wasn't growing continually. It was growing in little discrete steps. So after 1 year, the money gets added in. And then here, it's still growing in steps, but the steps are smaller. You add money, you add money. And then 12 times a year, you still add money, you're just adding it more frequently. But it's still getting added, if we were going to graph it, it's still getting added in little stair steps there. If you're growing continuously, the stair steps are becoming a smooth curve. And so that's continuous growth. And a lot of things can be modeled with continuous growth. And a lot of natural processes also involve continuous growth. So that's why E is important. It's not really about investing money. Money was just a nice context to help us think about what would it mean to grow continuously. All right, I think we're going to stop it there. If we wanted to relate this back to money, there's more things that we could think about, because we might want to add some things back into our scenario. Ideally, we'd like an equation for the amount of money we have if we're going to invest not $1, but P dollars, and not 100% interest rate, but an interest rate of R, and not for 1 year, but for T years. Like, could we have an equation that involves all of these things? And the answer is yes, and it involves E. And if you want to think about it, you might be able to derive it yourself, but we will leave that for a future lesson.